All right, folks, let's get started. I did not realize it was week 6. I thought it was week 5. That was news to me. Where does the time go? It's a rhetorical question. I don't know. I changed this all up. So this week is obviously check-ins. A little less than half of you have sent me Slacks or messages to get check-in times. You will want that number to be higher. We're going to try and get through the end of conservation laws today and right into computational fluid dynamics. And then I'm going to do this really annoying thing. I'm going to go back and forth between the 2 chapters in order to give you some feel for the technique. If you've read any of chapter 6, that would be helpful. If you've never coded before, you are in for a little bit of a shock, but it is fine. Computers do what you tell them to do. So when you get mad at the computer, inevitably, don't worry, that's your fault. And the homework this week is going to be really fun, in my personal opinion. The first 2 are less mathy and more learn how the fluid works by physically playing with fluids. And the third one is computational. So you will need to download Python if you haven't done that already. All of the class will be in Python. If you've never coded in Python before, let me know. And I'm happy to sit down with you in an office hour and give you the rundown. Question before we start? Okay. Oh yeah, here we go. I should have had this up. Okay. So this is what you'll do eventually. This is boiling water. So not my boiling water. This is just boiling water. And you see that the simplest approximation is 2-dimensional. And here you have a heating element at the bottom. At the top, you have a cooling element. You have boundary conditions on the walls. We'll talk about that more in detail when we talk about the computational fluid flow. And then just naturally, you have these places where fluid will start to seep up. And those are self-perpetuating. This is called Rayleigh-Bernard convection. Rayleigh has a name on fucking everything. What are you going to do? So these are the check-ins. We're going to do them this week. I think Orlando's not here, but that's okay. He's the first check-in. Oh, you're right there. Oh, yeah. It's like, whoa, okay. If you haven't set a check-in time with me, just send me some times. And then when I say no a bunch of times, I'll just screenshot you my schedule and you could slide in there anywhere. I have a check-in tomorrow at 8 p.m. So I'm happy to do them by Zoom as well if your work schedule sucks, because I know that a lot of people are also working. Questions about this process? Anyone nervous? That's why you went first, to get it out of the way with. Okay, so let's do one thing really quickly. Let's write down a couple equations, and I realize I should have started with this as a maybe this is the first time that we could have done it. We're gonna write some things down every single class. Okay, and then I'm gonna call on specific people to explain not the name of it, because remember when people say, oh, advection, that doesn't mean anything. You have to describe what it means. You can say the name as well, and I'm sure your fellow students would enjoy that. But let's just go through this process of making sure that we know what each of the terms are. And then we'll talk about energy today, and then we'll talk about computational fluid flow. Maybe we'll write it. That's the right. Okay. Break this. Okay, what is this, Rolando? Not each term, just the name of this. That is the continuity equation. What's the first term?
That is the steady part, and it's the rate of change in the density.
Right. The rate of change in time of the density. Very good. Alex, the
change in the change in the fluid, flow
Mhm.
in space,
Mhm.
or the, sorry, the divergence.
Yeah, so this is, we call this the flux divergence, that's correct. But there's, what you're saying is fine too. What's another word for this type of term? Eduardo?
Divergence of the mass density.
Yeah, divergence of the mass density, definitely. Is there another word for this type of term? Read? Good. No. The momentum. Not quite. These are together, but that is not what this equation is talking about. Jose? He already said flux. Oh, what? Nope, there's no strains here. Toby? Okay, Desmond? There's no pressures here. This is bro. Isabel? Divergence of the mass flux is the right idea. There's another word for divergence of a quantity.
I'm just thinking of that thing where you said like when you were eating a lot, it tells you what you're consuming.
So right, so that would be this term, right?
Okay.
This is me eating a lot, and then what happens to me?
You get
I get fat, and what is that called? That's the divergence of the mass flux, that's true. But there's two words for these terms. You mentioned that these are steady terms, and this is the
it's like the amount.
what?
Advection.
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 Okay.
You were thinking the same word. You're thinking the same.
Damn, we almost got it. We're in the whole class. All right. And that's it. It equals 0. Mass cannot be created or destroyed, at least in this classroom. Of course, in real life, it is often, but that is not in the scope of the work we're going to be doing. Okay, so now we're going to write the harder one. I heard a lot of explanations for terms that were not present, so that's okay. Let's write this one. All right. So since the front well did really well last time, we're going to start with the back row in reverse order. What equation is this? What's that? Okay. Okay. Isabel? Okay.
I know it's the total derivative.
No. What is the whole equation?
It is.
We're gonna do it term by term. Don't explain the terms.
Okay.
Everyone's getting an opportunity. First question is just what is the equation? The first one was the continuity equation. The second one, you already did this. You're done. You have no more answers to that. You're very close.
Okay.
Yeah. It is the Navier-Stokes equation.
Okay.
The reason that it's not the constitutive equation is because the constitutive equation describes how stresses and strains are related to one another, and they take us from our definition of T to our definition of S and R. This one here has all that funny mu stuff, And so once you've included that there, then your equations of motion, your conservation of momentum becomes named after a person. So the top one is conservation of mass. The second one is conservation of momentum. Okay. All right, so what's the first term? Jose? Sorry, this one here.
Or the change in the velocity over time of the fluid density, or with respect to fluid density, or? Yeah, that's a little trick. How? The next one.
Kobe?
It's the change in the mass with respect to space and time.
With respect to space and time. Right, so what does this big E mean? Yeah, total derivative. So it's the total derivative of the momentum. Rho has come out. Okay. All right. Read what's this term? What's that? Pressure. Pressure what? Change in pressure. What are we talking about here? What is this thing doing? So this is the change in the momentum, and this is there's another word that we would use here. What's that? What do gradients mean? Pressure is not just a thing. Pressure is a pressure flow. Right, so I would say pressure force here. This is the pressure force. What is this one? Oh, someone knew? What's that?
Body force?
Body forces. Okay. What is this one here? That's right. We're gonna do this at the start of every class now. So don't worry, I'm gonna call on people specifically and they're gonna answer about the different parts of it. I know you're warming up a little bit, so this can warm you up. What does this one look like? This is a mu, and then this whole thing, what does that term mean? What does it like physically say? Yeah, it definitely has to do with the velocity. What is it physically meaning there? Yeah, that's a good question. What does the mu mean? Yeah, anytime that you see mu or mu nu, these are bulk viscosity here or the kinematic viscosity. And in this particular circumstance, we'll note that these are in a certain direction, which means that this piece here is not acceleration because this is changing with respect to x. If we're double derivative with respect to time, then you'd say the acceleration velocity. That's not what this is. Yeah. Okay, what does that mean?
Are we seeing something that is maximum?
You're definitely interpreting the thought of a double derivative correctly.
Yeah.
But the physical interpretation of what it means here in the fluid is missing. Okay. Steady's over here. Right, the steadiness is on this side. These on this side, this is how the fluid changes with respect to a single parcel, and this is why it changes. We've talked about it changing due to pressures. We've talked about it changing due to body forces. What is this term? And you can see all of these terms, they must be related because they all share these weird mu things, right? Yeah. Say that again. Location. Yes, this is changing due to differences in something to do with the location, but there's a reason why viscosities are in here. This is the part that was in the stress tensor. This is in fact the stress tensor. And the first term in the stress tensor was? Well, yeah, there's mu strain. What kind of strain? There's different, yeah, the diagonal terms, and then the off diagonal terms, right? That sucked, right? It's okay. So we're gonna do this every single time that we start up, and you're gonna be like, "Oh, I get what they all mean." It's all very dumb, bad math, but it's very approachable. Once you understand gobbledygook that's up there, it will make sense. Okay,
What's the rest of it?
what's the rest of it? Diagonal terms?
Yeah.
Okay. I would have also accepted. Okay. Questions?
So with the mu, so mu v is bulk viscosity?
And that is defined weirdly. So, okay, remember that fluid descriptions in particular are not passed down on high, right? The description of fluid flow is not something that was given to us on tablets. It's empirical relationships and some first principles derivation. So this first part here, we derive because we make assumptions about the fluid. The second part here is empirical, in particular, this piece here. So what we do is we make these equations and then we test them. We put fluid through a pipe and we say, hey, that mostly did what we expected it to do. And if that's the case, then maybe we measure this thing here, right? We say there is some relationship between the double derivative of the velocity with respect to space and some unknown parameter mu, and you measure that for a fluid. And it turns out that the different ways that you measure it in a fluid, the different directions, have different quantities, very stupidly enough, okay? Because fluids are weird. Okay, so you're asking yourself, very important question. Well, Mateo, I see that we have 3 components for the velocity. So I have x, y, and z. That's going to give me 3 components of the momentum. I have 1 equation for the pressure. Sorry, 1 equation for the density up here, and then I have this weird thing, pressure. Right. So unless we're in a situation where the pressure only depends on the density, that's the only time that you need only these 2 equations and you're done. Otherwise, you need energy. Come on, why is this not working? Hello, please. Okay. So you need a caloric equation of state. Caloric is not Dr. Calori. This is of calories. And essentially what we're talking about is the conservation of energy on a fluid parcel. My book though. Oh. Okay. This is going to be fairly straightforward. Very intuitive, and everyone's going to say, oh, I would have guessed that, right?
Mm-hmm.
Okay. So in fact, here's how we write 4.46. What the hell did I just write? Not reading from your books, understanding what you've seen. It's not about getting the answers. Remember, you're not even getting graded in this class. The idea is do I understand what the fuck is on the board? Yeah.
So I know at least on the right side, you're doing a volume integral of the body forces dotted into the velocity.
Bingo. Anytime you see that G on there, you're like, body force. Got it. Nailed it. Right? So if you recall, when we first were talking about the Reynolds transport theorem, we said, fuck the math. It's really horrible. I don't really care how it works. But what I want to think about is this Amazon parcel. And in general, I'm going to use the Amazon parcel. I'm going to start with an integral form of it, control volumes, Amazon parcels, and see how stuff moves through it. So on the left-hand side, I would look at the time derivative of the thing that I wanted to conserve, or the thing that I wanted to observe, right? In this case, I'm thinking in my head energy, because I just told you, but what about energy? So this is in fact saying on the left-hand side, the volume integral of that thing. And then correctly speaking, this is the body forces on the entire volume, right? Very good. So that's one term. Other terms.
So that F there is surface force, right?
Yes. Well, the force on the control volume surface, right? Any internal forces are not going to be captured. Okay? So if I push my sphere of fluid, that will give it energy. Does that make sense conceptually? What's this one?
The heat loss.
Heat loss. Okay, so I would say something more generally, right? Which would be heat. Exactly right. So heat flow or heat transfer, because we don't know if it's positive or negative. Usually we think of it in terms of heat loss, but a negative heat loss is a heat gain, whatever one you want to do here. And that's that fun Q, right? And that is through a surface area. So if you've taken a class with me where we talked about, for example, the loss of heat through a sphere, right? That goes through the surface area. The content of heat is in the volume, right? And you see that up there. So what's that shit on the left-hand side?
What was the first one again?
That's my question. What is this one?
No, I mean, the first one we went over.
Oh, this one here. What's this one here?
This one.
Body force over the volume.
This is the body forces on the whole volume. Second one is
Surface forces.
surface forces on the parcel. And the third one is heat flow through the exterior surface, right? So imagine I have like, have you seen those like when people can get into those bouncy balls? Okay, so imagine my buddy's in a bouncy ball, right? I can do a lot of things to it. I can take that bouncy ball, I can put it on the top of a hill, right? That's this piece. So I take the whole volume and I put it on the top of the hill. And then I push him with my hands on the exterior, right? And then, maybe just to really mess with him, I'm also gonna like put a heater on the edge and pump hot air into the volume so that he gets really warm when he's going down the hill. I don't know, it's an example. So what happens on this side, inside the volume? There's one quantity that looks really familiar to a lot of people.
Kinetic energy.
Where is it?
1/2 the velocity, right?
Right, 1/2. Anytime I see a 1/2 in something squared, oh, it's kinetic energy. And in general, that's pretty true, right? 1/2 u squared is the kinetic energy. Okay, so this is the kinetic energy right here. What's that? Yeah, E, but is this an exponential or
Is it that two number?
is it 2? That's what I'm asking. Is it 2?
About.
No,
Oh, shoot.
it has a meaning. Yeah.
Is it energy on one part?
Yeah, so what's a different way of saying that? It is energy, certainly, because we're talking about energy, but what type of energy? Yeah. Why is it the internal energy?
The energy within that parcel of fluid, or
Yeah, why is it the internal energy? What gives you the hint that it's the internal energy?
is it inside the volume integral?
Right, it's inside the volume integral. How would I write the total energy?
Oh, U plus.
Big E.
Oh, okay, good.
How would I write what is the relationship between big E and little e?
big E is total, right?
What's that?
Big E is total.
Yeah, that's total. And this is intrinsic energy. What's the relationship?
E over rho.
E over rho or E over E sometimes? Right. It's the specific energy. Okay. Internal energy. Does that make sense? Okay, so what this is saying is I can either increase the kinetic energy or I can increase the internal energy. Okay, what does internal energy mean again? What?
Heat energy.
Yeah, so how would I interpret that like with other quantities that I know about an ensemble? Let's say I have my Amazon package again. If I increase the internal energy, what increases?
The kinetic energy of the components.
So the kinetic energy is separated here, right?
But that's the kinetic energy of the entire person, right?
Mm-hmm.
So like kinetic energy is atoms.
Okay, you're very close here. So what's a different way we say that? Individual kinetic energies increasing means thermal energy, right? It's the connection between individual molecular velocities in arbitrary directions, not contributing to the bulk flow, right? So you're saying those kinetic energies in general all go up. They're averaged to increase the temperature. So essentially here you're looking at something that represents a combination of many factors, including temperature, right? That's the internal energy. And this is the bulk flow, right? It's normalized. That's what those aren't just lines. Those are absolute values. Okay. You did it. I wish I could. Okay. What did I want to say here? So we can write this. I mean, you can go through the process if you'd like, but we can write this on the bottom there. It's only going to take me, well, yeah, let's go through the whole process here. Why is this not moving? What did I do? There we go. Okay. Okay, so starting with the momentum equation, where it's 4.22, which is over there. You can make equation 4.56. And what I want to do here is I just want the kinetic energy equation. So I want to know what this thing is like in here. Okay. And I can do that with, where'd my, all right. Yep. Let's see if I can write this properly. Did they hide the erasers on purpose? I don't understand. Is this 3 on this side?
Oh.
All right. All right. Okay, so what the fuck did I just write?
It's that big, it's up right.
It's that?
No, just looking.
Oh, okay, so a very serious question. What did you just write? This is supposed to be tau. What was the tau again? It's the stress tensor. So instead of writing it out like all that, I just made it really simple because we're just going to try and not care about that for a second. So what did I do here? How did I get 1/2 uj squared? What? That is the kinetic energy. I'm creating a kinetic energy, but from scratch. Yes. I took one equation, I did a little something, and I got this equation. What'd I do? I took that equation, I multiplied it by not kinetic energy, but by U, by one factor of U. If you look over there, this is the same factor, just multiplied by U. This over here is rho G with U. And this over here is just U times that thing in the front. You see that? So I can use this combination of this equation on the left-hand side, which is the momentum equation, just multiply it by another U, and I get a faux kinetic energy equation. Does that make sense? Okay. Does that make sense what they mean?
Then what happened, you just multiply them.
Yeah, that'll come out later, doesn't matter. No one gives a shit. It'll be absorbed in ways that you'll see. But what is important here is, what does the kinetic energy depend on? What's that? Yeah, so remember over there, we said that you could change, for example, the momentum of the fluid, or you could change the steady and the effective part of the density. What does this tell us mathematically? Here we have something called a total derivative, right? What does that mean again? What's that?
Change in space and time.
Change in space and time. So there's an unsteady term and there's an advective term. So the first part says the unsteady term is telling us whether or not the kinetic energy is changing with time, or how the kinetic energy is advecting through the fluid, right? So that's this first part. What does this mean? Body forces. How are the body forces communicated to the fluid as a whole? Like this one. Pressure forces. How are the pressure forces communicated to the fluid as a whole?
Stress.
Stress forces. Another word of saying that is. What's the mu mean up there? Viscosity. How are viscous forces translated into the fluid, right? And that's what I wrote. Body, pressure, and viscous forces. These are the things that change the kinetic energy of the fluid. The way to think about that is that it is a negative gradient. So pressure is going to go from high to low. Yeah, so if it's a negative gradient, instead of going from positive to, sorry, from low to high, giving you a positive contribution, here this is going to go from high to low. That's going to increase your velocity. You see that? So this slope here is negative, then the negative negative makes a positive, and the kinetic energy goes up. Yep. If this is negative, then the negative negative makes a positive, and this goes up. Because this side here is plus when that's plus. If this is positive, meaning the normal way, right? Then the negative is going to take away from the kinetic energy. Cool stuff? Okay. So now we can take the difference between that and that to get the well, the other version of that, to just get the total derivative of the internal energy. I'm not gonna write what the original one was, but you're gonna believe it. It's gonna look sorry. It's gonna look like this. It's all in your book. Hold on, I have to draw this really well because this is like that. That kind of look like a V, but it's not quite a V. Small V. Okay.
That'd be parties.
Excuse me.
Why? No.
That's rough, right? It's drawing for 2 seconds. So what are we talking about here? What's the left-hand side? All the way on the left-hand side? Say? You already did this one. You can't go again. Can't be your answer for everything in time C is D.
Total derivative of the kernel.
This is the total derivative of the internal energy. Okay. What's the second part? Do you remember in week 1/2, whatever it was, when I made you do all the stupid thermodynamic stuff? You remember? And you're like, why? This isn't connected to anything. This is why it's connected. Oh, what is it? What? There isn't density here, actually. Yeah. It is a V, yeah, but it's a weird V. It's specific volume, yeah. Volume times pressure is a.
Oh, NRT.
Yeah, it's NRT, isn't it? Work. Isn't PV work? Right? So this is your PV work. Right? What's this?
What's the stresses again?
But how do we think about them in terms of the internal energy? It's definitely a stress term, right? Anytime you see tau, that's a stress. But when I see stress now, I kind of want to think more in terms of what it really means in a fluid. It's maybe I'll write it over there so it's easier. There's no rotation here yet. I'll just believe it only because you got it right earlier. What's another way of writing this? Stresses or strains is the how the fluid moves. Stresses is what gives the fluid motion. But this is all moot if you lack this one thing your doctor doesn't want you to know about. Viscosity. Viscosity, in fact, if you don't have viscosity in a fluid, you can't communicate any of these internal stresses.
Okay. I was like,
It's like one of those things where you know, like this one thing, right, that your doctor doesn't want you to know about.
Yeah.
That's just autofills in my brain, and I say it because there's no filter. There's no filter here. Does that make sense?
very viscous.
Yeah, very viscous. So over there, you see that stresses are communicated by viscosity, right? So here's a different way of saying it. You see some strains, you see some stresses, right? You see some nice little tensor boys here. What is this?
They're just viscous.
Okay, so yeah, viscosity, but what does that mean? What are we talking about here? On this side, we talked about the change in the internal energy is due to PV work and
Distance work.
viscous work. What? What's viscous work? That would be taking energy from you. How does it put it into the fluid? Friction. Okay, that is what viscosity means. What is happening here? Remember what the E meant? Yeah, internal energy, that was what?
That's the energy transfer due to viscosity.
Yes, but we're all saying the right words here, but I want to think of it conceptually. Okay, what would be a physical example of this type of viscous work?
So like when you spin a bottle and there's flow inside, if there was no viscosity, the water would just stay still.
That's only momentum though. right? That's describing the momentum shape. That's good, but that's only momentum. I'm talking about how the internal energy changes. Right here, we had how both of them change. I want to think about this change in the internal energy, and we said that the internal energy was a representation, usually in terms of you have a big fluid. The internal energy is represented by little e. Okay, let's go back one more step. Let's walk it back one more step. So we have the kinetic energy of the whole box, and the internal energy per particle is represented by a distribution of the velocities, which we call thermal. The thermal energy. So here I'm saying the rate of change of the internal energy, the thermal energy, comes from different places. It comes from PV work. I already knew that, right? That's that's your PV equals nRT, and then you change the temperature. You see it?
Yeah.
Okay, what's this? Viscous work. How does it change the fluid?
Friction warms the fluid.
Friction warms the fluid. Okay. If I do this, there is a layer of water between my hands that is certainly getting heated, and now my hands hurt. Okay? Do it. I promise you it will work. Do this really quickly. There's like oils on your hand, and you'll feel them afterwards. Right? You just burn this top layer of your skin off. What are you doing? You're taking kinetic energy. Okay? You're rolling around a fluid in your hands, and through viscous dissipation, it's heating up and making your hand warm. Pretty cool, huh? Okay. What's the last one? Yeah, don't smell your hands. That's not required. The last one's stupid. The last one's heat flow. Okay, and let's be a little specific here. What is the real heat flow that we're talking about here? It's not just heat flow, there's something specific here. I like where your head's at. I just meant this thing.
That certain direction.
So when I have these repeated elements, another way of writing this is the
Summation.
what? This is the gradient of
Oh.
right? Okay. All right. Okay. Success? Everyone happy? Yeah. So it is a transfer of energy. Okay. If there is viscosity in the fluid, you're always going to have those viscous forces dissipate energy into the internal energy. Hated that. Okay. Let's say that again. Let's say that again. Can think about it conceptually, right? You have a fluid, and what are you really talking about when you're talking about this type of thing? You're talking about sort of first weak ideas, which are that in between a fluid, you have a bunch of individual molecules. And it's the way that they bump into each other, it's the way that they adhere to one another that makes a fluid flow differently. So for example, ketchup flows differently than water. And that's because of the intermolecular like separations and the way that they interact with one another, right? Okay. That's all sort of carried in this term, and it's hidden. So we say, for example, for a Newtonian fluid, that they're linear. They don't have to be linear. You could change those terms in there so they were non-linear, right? You can put, instead of u, notice this is u equals to 1, but a u to the n, it would be a non-Newtonian fluid. Does that make sense? And then you would just test it. You see, does it behave that way? Oh, in fact, it does. Okay. So what I've hidden in there is what's actually happening in the fluid. And that's the transfer of momentum and also energy. Now, conceptually, when you think about a fluid, you heat up a fluid like water, okay? It just gets taken out and you can't get it back. Does that make sense?
Yeah.
Of course, there's ways to extract heat from hot water, but that's not what we're talking about here. Okay, those are not fluid equations. In general, when we think about the transfer of energy, it takes water out of the fluid. Sorry. It takes heat out of the fluid and puts it into average motions of the molecules. Okay, so if I walk through this again, ready? This first one here is the rate of change of the internal energy is equal to changes in the volume on the pressure. So I take my box, I make it larger, and that's going to change whatever the pressure was in there. It's going to change the total amount of internal energy. Does that make sense? So take your Amazon box, make it twice as large, same number of particles. What's their thermal energy now? Down by a factor 2, traditionally, right? Okay. Over here, I take my Amazon parcel and maybe I push on the top of it and I do this a bunch of times. And every time that I do this, I'm heating it up. And I'm warming up the internal energy. This hand, not moving. I'm not contributing to the flow. Right? So if I do this and I don't move the parcel, there is a fraction of this motion that is converted into the heat in the parcel itself. Doesn't contribute to the motion of the parcel. Remember, that's over here. Or fucking right above me. That's over here, right? This is the motion of the parcel. This is the internal energy of the parcel. C'est bon? Okay. Last part here is the gradient of the heat flow. This one makes sense. Okay, you have some heat flux. Point a radiator at a fluid, temperature goes up. Okay, and so when you boil water, you're going to have a box like this, and you're at the very bottom, you're going to create a heat flux. It's going to permit heat to enter the fluid, and then it's going to distribute itself however it wants. Okay, so that was the mechanical energy equation. Oh, maybe I went too far here. I wanted to talk about viscous work. Maybe I already did this too much. That's all right. So this piece here, one of my favorite things that physicists do is when you see something that you don't like, just call it something else. So we're going to call this piece here the viscous work. We're going to call it Ada. Okay. That's what it means, but that's the definition. That's the definition of viscous work. And it's the product of the viscous stress acting on the fluid element and the deformation of that fluid element. Okay. So you can rewrite that however you want, but basically it's important in turbulent flow. So when we talk about turbulence, I really hope that we get to turbulence in this class, but the thing that you want to know right now about turbulence is that the process of turbulence as a whole is the process of extracting kinetic energy from bulk flow and placing it into thermal energy into the fluid itself. Okay? Do those words make sense? I see about half people who are awake. Okay. All right.
So turbulent flow is slower.
Can you say it again?
Yeah, so turbulent flow, so I heard, is it slower? Essentially what it means is you're extracting flow and you're putting it into the internal energy. So the idea of it being slower is a little tricky because let's say you have, and let me give you an example, okay? Here's a rock, perfectly drawn rock. Oh. Hey, Giselle, you can even see this part. Sorry, I didn't even realize. Okay, perfectly drawn rock, and I have fluid flow. Okay, so let's say I draw some streamlines. Okay, and this streamline goes around like that, and this streamline goes around like that. Okay, a very bad streamline drawing. Don't worry. So in this particular circumstance, as I go around the rock, In this region, what happens to the velocity? Why does it increase?
Slow down before the pop. It wants to,
Let's imagine there's a tube.
it's the fluid's denser.
I'm gonna assume that I can't change the fluid density.
Well, like. Because the area flows through is decreased.
The area that it flows through is decreased because there's an obstacle in the way. So it only has this much space to get through. Whereas before, this much space could get through. And that is a principle called, it's written on the board. Don't look too far to the right. I don't know what that is.
Please don't break it.
No, hold on. Don't, it's not written on this guy. It's this thing here.
No.
It's the continuity of mass, right?
Yeah.
I can't make new mass and I can't get rid of it. So it sees here a little bit of extra parcel and it says, oh, in order to get past that and not pile up, I have to go faster. So the mass flux through any single location here is constant, assuming it's a constant pipe. Okay, so that was the easiest example. The fluid flow gets faster. But now, let's imagine that I keep increasing the velocity of the flow. And now viscosity starts to matter. And we'll talk about this when we talk about dimensionless scaling in a little while. But essentially what you'll end up getting, and this is something you've seen before, are these. Right? They kind of fuck up your idea of a streamline. They're no longer perfect. It's an unsteady flow, right? So in fact, these do this. And you get these things back here. They're called eddies. Kolmogorov, I don't know if I can say it today. Kolmogorov eddies. And what they're doing is they're taking bulk flow left to right, and they're transporting it. If you look in the size scale of these eddies, let's say you had a little microscope and you zoom in here, then you would see that these eddies go like that. All the way down. Get smaller and smaller and smaller, eventually just thinking about warming up and moving past specific molecules. So when the fluid moves together, that's great. Intermolecular forces don't really matter. If you nail down really far into the fluid, then the particle forces matter. And if you have two particles going the opposite direction, they'll collide into each other, so to speak, right? Right? Okay, so this is turbulence. We will not talk about this for a while. Okay. Yay, that's tricky. I don't like it. Okay, but the important part is here that when viscous work is important, it's transferring kinetic energy from the bulk flow into internal energy in the fluid. Okay.
So if there was something without any viscosity at all, it would not be turbulent.
Correct. Yeah, that's a wonderful implication. Yeah. Yes. Absolutely. And this is why, yeah, the ball can be anything we want, except there's no walls, or we don't traditionally think about them as being walls. We will talk about wing design. You want to know why planes fly? It's pretty straightforward, but essentially it has the same phenomenon. The boundary conditions are slightly different because you're flying, but essentially the attack of the wing here, if you change it like this, you divert flow over the top, divert flow under the bottom. There's a pressure differential that causes you to go up. Okay. Yeah. Questions? Yeah. Okay. Some people you'll see on TikTok that people will be like, oh, one way that people talk about planes flying is the Bernoulli equation. Some people talk about Navier-Stokes. Actually, we don't know anything. That's wrong. Okay. The best thing about fluids is we do understand them very well. They're just much more complicated than any one equation can describe. So in fact, we've already had 3 equations to describe nothing. We haven't even talked about a fluid yet. right? We've just talked generally about all fluids. So when you talk about something as complex as aerospace engineering or aircraft engineering, you use all of these equations and then you put it onto a computer, right? And it gets harder, okay? But in fact, yes, we do understand how planes fly and why they fly. Anyone afraid of flying? I know. Anyone else afraid of flying? Okay, my
Me.
favorite analogy for flying is, you're in this fluid and you can't see through it, so you get really scared. I shouldn't go on this tangent. But you saw in like everyone's watched The Office, and then Jim puts, or what's his name, Jim? Yeah. Puts the stapler in Jello, right? And it's sort of suspended in Jello, and you shake it. That's you in the plane in the air. Okay? There is no opportunity for the air below you to disappear. Okay? You're doing this, but you're still got air on the bottom and air on the top. You're suspended in a little sandwich of air. Okay? So it's scary, but it's not that bad. What? How many times has that happened? I'll ask you. Get a car accident on less than a week ago. I can guarantee you're more likely to crash on your way to your airport and die than you will for your plane to go down. All right. Yeah. I can avoid it. Okay, so every time that I travel now, I always bring a parachute just in case. That way I always have the agency on the plane to just jump off if things get hairy. Okay, we've gotten really off topic here. Okay, so let's just finish this part here because this is a really important part of the energy equation. And that is, we talked all about entropy. What the fuck was entropy again? Close. There's a different way to say that. Yeah, something about disorder. Disorder always increasing. At a minimum, it can do what? No. It can always go up. In the best case scenario, it can stay the same. It can be the same or it can go up, but it can never go down in a closed system, right? In an outside system like humans, you could become, of course, more advanced, put together random objects, make them into thoughts. Fucking knows. But the important part here is we didn't see that at all. Right? Where's the entropy in these equations? What?
That's only internal.
I know, but this is the internal energy. I'm trying to describe the internal energy, and now I've pulled the switcheroo on you, and I've never talked about entropy. So you shouldn't trust this, right?
So is this a good approximation?
Well, this is a good question. I mean, do I have to start all over with a different entropy equation?
Add something to the total.
Wait, where? Here?
Yeah.
You want to add another term here, an entropy term, but entropy is not energy.
Is it like the work differential?
So that's traditionally how it's written in terms of like S equals P NL something something. But conceptually speaking, we don't have an S here, right? I mean, that's wrong. There is an S here. This is a different S. That's not the S we want.
Like entropy is the most likely state, right? Does that help at all?
Entropy is the most likely state, yeah. So any statement that I made that would guarantee that entropy conservation is there? Always increasing or staying the same?
Oh,
Yeah, is there something that I wrote in there that is secretly telling us that entropy is always going to increase or stay the same?
gradient of the heat flow.
Say that again? No, because heat flows don't have to be entropic. Right? Think about it this way. You have a heat flow from this point to this point. Okay. That might just redistribute the heat, but it might not change the internal temperature, right, of the whole system. Viscous term. What is the viscous term doing?
This term is never zero, so the.
Well, the viscous term can be zero. Yeah, if I let it be zero, right, then it would be sort of a boring fluid, and you would say that there's no viscosity, there is no change in the entropy.
But is that just like super cool helium and stuff like that?
Yeah, those are the only things, right? So in general, when I speak about every fluid, what am I saying? There's a time reversal asymmetry here. You cannot watch the fluid backwards without knowing that it's flowing backwards. In fact, when I watch something like this and I play the video in reverse, these will all unspin and they'll go this way. And you'll know that's incorrect. Inherently, you know the arrow of time because that's part of our souls, right? We see things. If I drop something that will break, right? Right? I can't play that backwards without you disbelieving that it happened, right? The same thing is true here. This viscous workpiece is satisfying the second law of thermodynamics, and it's doing it without us having to worry about it. Oh, thank God. Right? Because I fucking hate entropy. Does that make sense? Okay, so I have both laws of thermodynamics in there. First law is where? What was the first law of thermodynamics?
Yeah, those are-
Energy equals work plus heat flow.
Yeah, perfect. It's right here, right? Work plus heat flow. It's written on the board. So even though that stuff was really long time ago, it all mattered. Amazing. All right. Oh fuck, we never have enough time. Why won't this work? Okay. We're gonna jump right ahead to a specific version called the Bernoulli equation. The best part about the Bernoulli equations, there's 4 of them. There's 4 Bernoullis, not there's 4 Bernoulli equations. So you might see very often that Bernoulli is named a bunch of different things. You don't know which Bernoulli it is. They were like all family members, and I forget how it works, but there was like one successful physicist, and then like his son was successful, and then his son was successful. There's like 4 Bernoullis, and they got all this shit named after him. So I don't know which Bernoulli this is, but essentially what we're going to do is we're just going to start with something very straightforward, and we're going to look at that equation over there, and we're going to imagine that it's inviscid. What does inviscid mean? No what? No viscosity. So that's easy. So that whole term on the end is gone, right? And I just have this P dP dx and this rho g term. And the rho g term can be written as the gradient of a potential, right? So I could write something like this, gradient of something called phi, and then it'd be generally solvable. You can make it easy on yourself. You can ignore anything that is electromagnetic and just only work with gravity. I think that's the right move here. What does the word barotropic mean?
Is it same pressure?
So that's isobaric. So it does have to do with pressure. Good, we got part of the word. The bar does have to do with pressure. Barotropic, barotropic. What do these words mean? The same word. What's that? Very close. That would be constant pressure would be isobaric. Okay, barotropic just means that density and pressure only relate to one another. They don't depend on temperature. Okay. What does baroclinic mean?
Isn't the barrel line being line and a constant pressure on like the ground volume, temperature or something?
Yeah, those, so the Kleins there, okay. Yes, in the way that Kleins work, like a thermocline will be a line of constant temperature on a map. But what would it mean if a flow was baroclinic?
Is it like another relationship where pressure and something else are the only things related to it?
You're on the right path. I wonder if we should do this here. I don't really have enough time. I didn't realize this would take so much time.
Yeah, the book is really helping.
No, it's not the book that I'm worried about. It's that we could do Bernoulli's right now, but I kind of want to start you on computational. No, right away I have it. We're gonna come back to this. I know this is in your equations. You're welcome to read. I would just start with Bernoulli's equations in the special forms. You don't have to go that far to understand basically what you learned in the 2500 series, which is talking about how the relationship between pressure and gravitational potential are interchangeable as long as you make some approximations, such as the fluid is viscous or not viscous, that the pressure in the densities are related only to each other. It's isentropic, for example, not changing in entropies, right? So the fluid flow can go both directions, time reversal symmetry. Once you've done all those things, you get these really simple equations that you can understand flow with. But I don't care, okay? Because now we get to the best part of the class. What is wrong with this computer? I'm going to scream. Everything is broken and nothing is happy. Okay. What? It is all the time. My computer like breaks like every week. Okay, so let's talk about computational fluid dynamics. This is really important that we start thinking about this right now. This is chapter 6 material. If you've never used the computer to simulate a fluid before, congratulations. You're probably in the majority. If you have, you probably did this in my fluid dynamics or my computational class last semester. So people who took computational last semester are in a better position probably than people who took it a year or two ago, because they need to like dust it off in their brain. So I'm gonna encourage you strongly to look at this material very closely because it will get complicated fast. To solve almost all problems, you need a computer in fluids. Everyone who's anyone uses a computer. You start with these 1, 2, 3, 4. There is a version that puts these together, but that gives you all of the things that you want. Here I have a constitutive relationship between the pressure, the temperature, and the density. I didn't show you in detail, but it is there. This is how the internal energy is changing, okay? The internal energy relates the pressure to the temperature. The temperature is shown here. Up here, this is how the bulk flow is changing with all of these ones. So I have plenty of equations. They all relate to one another, and they can totally describe the motion of the fluid. You can only solve these in very specific circumstances analytically. And this whole book is dedicated to those special solutions. So everything after here, right? This whole piece is just special solutions of these equations. Okay. It says what happens if you get down to the boundary layer and stuff begins to convect and pull. What happens when material pushes into one another and those shock forces aren't a good approximation anymore. Right? That's the rest of the book. But for everything else, you need this. It's a computer. Okay. So we saw this type of flow, right? Maybe you have a fluid coming in, and as it goes in, the pipe gets bigger. So here the flow would be going faster, and here it would slow down. But how does it actually change after that? If it's continuous, well, you need a solution that you find on a computer. And it's very straightforward. You just make an array. Okay, let's say it's a two-dimensional array, like that. Okay. And then I'm going to find at every single location all of the fluid properties. I'm going to find the density at every location. I'm going to find the fluid flow in all three directions, or maybe two if it's in two dimensions. I'm going to find the temperature, and I'm going to find the pressure in each direction. Okay, so all you need is like 8 different arrays, and then you just solve it at a bunch of tiny little spots. And you realize why no one did this for thousands of years, okay? Only possible with modern computing. I say simple, it's not simple. The implementation is straightforward. But of course, this didn't become possible until modern computing, okay? So you live in a very unique time period in fluid dynamics, because you can simulate boiling water on your computer. No humans have done this 100 years ago, yeah.
Random question, but for video games, do they use similar techniques as to
Yes.
water?
Well, for water, yes and no. First, they do the water modeling. So that's the physical modeling. And they do something called ray tracing, which is uses how light scatters, which is a very complicated radiative transfer code. But yeah, that type of shit is hard. Fuck, I already went over. Here at the bottom right, what does finite difference mean and what does finite volume mean? Know what those words are before Wednesday. And tell me what baroclinic means. And tell me what barotropic means. And tell me what isentropic means. Okay. What? No, we don't have time. I have to talk to Rolando.